Right. So in the part one of the video solving problems on the Michelson-Morley experiment, I had discussed about four problems. And in this video, I'm going to discuss a few more problems. So I start with the problem number 5 here. In the Michelson-Morley experiment, a shift of one fringe would result from a difference of one wavelength or a change of one period of vibration in the round-trip travel of flight when the interferometer is rotated by 90 degrees. So there is a typo here. Right. Had the experimenter seen a shift of one fringe, what speed Michelson and Morley would have computed for the Earth's motion through the ether? Now, for those of you who haven't watched the lecture video in this channel on the Michelson-Morley experiment, I suggest that you please do so. Also, for those of you who haven't watched the part one of the uh, solving problems on Michelson-Morley experiment video, please do watch it. I've given the links to both these videos in the description of this video, so please check out those links. So before you proceed further, if you haven't done so already, watch those two videos, please do watch those videos and come to this video. That would make things easier for us because expressions I will directly use from the earlier videos. Right. So the question here is, in the experiment, uh, one fringe shift would mean there is a change of one wavelength in the path of light. So the distance traveled by light, that is a path length of the light, changes by about 1 lambda if the fringe shift is one full shift. Or of course, time period, that is change of one period of vibration means time period of the wave, and that changes by 1 t. There is a complete change of the period of uh, there is a phase shift rather. That's what it means between the two waves by 1 t, capital T, where t is the time period of the wave. For a rotation of the arm of the interferometer by about 90 degrees, that is the statement here. Uh, Now, if the experiment had been done uh, where Michelson and Morley would have obtained a shift of one fringe, how much would the speed of Earth's motion through ether would be? That is the hypothetical question that is being asked here. So we can start from what is given in the question, that is one fringe shift for a change of either 1 lambda, let me call the wavelength as lambda, so it is 1 lambda, or 1 time period t, period of vibration is 1 t, right? So for rotation by 90 degrees, that is what it means, right? So now what is v? Because from our expression we know that the speed of Earth's motion through ether is v, speed of Earth's motion, that is what is asked here, right? So we have to calculate v here. So we know that del n is a fringe shift. Let us call that del n or n. It doesn't matter. That is 1 here. So we know that from our expressions that del n is equal to 2lv squared over cq. So please do check out the first part of the video, that is solving problems on the Michelson-Morley experiment, to understand how this expression is arrived at. I have discussed that in that video, as well as, of course, the lecture video on the Michelson-Morley experiment posted on this channel sometime back. Even that video contains this information, the derivation of this expression in a very simple way. So one can get that Now v squared therefore would be equal to uh, c cube over 2l. And that is 3 into 10 power 8 speed of light cubed. 2 times L is given as, not given in the question, but we know from the details of the Michelson-Morley experiment, 1887 experiment, that it is 11 meters. So that would mean 27 into 10 power 24, if we cube this, and this is 22. That would be v squared, right? So this is 1.24, 23, maybe 23 into 10 power 24. That is v squared. So if one fringe shift was observed, that would be square root of this, that is 1.11, let us say, into 10 power 12 meters per second. That is the kind of velocity one would conclude, because Michelson-Morley, in the Michelson-Morley experiment, they observed a much smaller shift. Because please do remember that they observed something like 0.01, that is about 100 times less than this value. So the velocity was much less for them, uh, velocity of Earth's motion through ether that they had calculated in their original experiment. Right, so let's proceed to go to the next problem. Yeah, so this is a problem. Number 6. Right. Paul and Peter can each row a boat at 5 feet per second in still water. They decided to race against each other over a course that is 2,000 feet across a river and back to the starting point. Paul rows across the river and Peter rows parallel to the direction of the river flow. If the river flows at 3 feet per second, who would win the race by how long? That's the question. So we have already done a couple of problems on the same lines. That is, similar problems we have done already in the part 1 of the uh, video, that is solving problems on Michelson-Morley experiment part 1. So please do check out those 2 problems as well. This is just for further practice and discussing something similar here. That is, you have a river that is flowing, and Paul and Peter are taking 2 boats, that is a boat for each, and then they want to row, and their capability is 5 feet per second in still water. Let us say Paul goes in this direction with his boat. Let us say this is Paul's boat, and let us say he starts from this point. Let us say Peter starts from the same point but goes in the perpendicular direction, that is along the river current, and river is flowing, let us say in this direction with velocity v, which is given as 3 feet per second. 3 feet per second. Right. Now, how much is the course? The course is 2,000 feet. So if they choose points on the bank, let us call that maybe point A and B here, and point A and C, the distance between AB and AC are 2,000 feet. The distances are 2,000 feet in each case. And yeah, now we can calculate. We have already done similar problems in this lecture, so we can say that I can directly write the expressions for Paul and Peter. The time taken by Paul, for example, to uh, go across. So Paul goes across, right, in the original assumption. So we say that time for Paul, T Paul, is equal to the distance is 2,000 feet over c squared minus v squared square root. So c squared in this case is in still water their velocity, that is 5. So it is 5 squared minus the river current speed is v squared, that is 3 here, 3 feet per second, so 3 squared, plus, of course, for the return journey also same. The distance is 2000 feet, L, in our original derivation, over this thing is 5 squared minus 3 squared again. So we can simplify that as 2000 over 25 minus 9, that is square root of 16, that is 4, plus 2000 over 4, that is 1000, right? This is in seconds, right? So time is seconds. This is for the journey across the river current. River current is V, direction of travel between A and B is perpendicular to it for Paul. Now let us proceed to calculate the time for Peter. Peter travels along the river direction, right? And then opposite to it later for the return journey. So here it is simple. L over C plus V plus L over C minus V in our original derivations. So this is 2000 over 8 plus 2000 over 2, and that is 2000 plus 8000 over 8 would it be, right? So that is going to be 10,000 by 8, that is 1250 seconds. So we can again see from this problem as well that Peter takes a longer time. He takes 250 seconds more than Paul. That means for the person who travels downstream or upstream in a river, he loses the race in comparison to a person who goes across and returns. So Paul, Peter. So Paul wins the race by 250 seconds because, of course, T Peter is greater than T Paul. So the time taken by Peter is more than time taken by Paul. So Paul wins this race by 250 seconds going across the river. That's the point here, right? Right. Let's proceed to go to the next problem. That is problem number 7. Excuse me. So problem number 7, in the Michelson-Morley experiment of 1887, the length of each arm of the interferometer was 11 meter, which is known from our lecture video. The experimental limit for the fringe shift was 0.05 fringes. What is the upper limit on the speed of Earth through ether owing to the null result of this experiment? So this experiment we know very infamously had a null result. And if the fringe shift was 0.005 fringes, the wavelength of light source used by Michelson was sodium source, so it was lambda is equal to 589 nanometers rather, 589 nanometers corresponding to sodium vapor lamp. Now, what is the question here in this case? We have to find out the speed, right? Because what is the upper limit on the speed of Earth? That is the question here. So let's proceed to do that. We know that L is equal to 11 meters in this case. We know that the fringe shift in this case is 0.005 and lambda is 589 exactly. It is in an earlier problem we had taken 600 nanometers, but for sodium source the actual wavelength is 589 nanometers. We know that the fringe shift is given by the difference in time differences del t prime minus del t over the time period of the wave t, and we also know that the time period is given by lambda over c. So if we proceed to calculate the time period capital T first, That is lambda is 589 into 10 power minus 9. That is meters in meters, from nanometer to meter conversion we have done here, over C, that is 3 into 10 power 8 meters per second. So if we do the calculation, we end up getting 1.96 into 10 power minus 15 seconds. This is the time period. Now del t prime minus del t is, we know that from our derivations, 2l v squared over c cube. And that is given as 0.005, from which we can write 2lv squared, because this expression we want to use these two expressions. So we say that it is c cubed over t, over c cubed t, that is equal to 0.005. So proceeding ahead, we can write what is v here, right? Directly, if I write v squared, rather, v squared is going to be equal to 0.0. We need v, right? So we can write 0.005 into c cube, because t we have written here, right? So it is fringe shift, so t over 2l. So if we simplify this further by plugging in the numbers, this t we have calculated here as 1.96 into 10 power minus 15. So plug in that as well. C cube is 3 into 10 power 8 whole cube. L is 11 meters. So if we plug in the numbers, we get v squared equal to 12.03 into 10 power 6, or v as 3.47 into 10 power 3 meters per second. That is the speed we are getting in this case. Right, so let's proceed to discuss the next problem. So this problem showed that in the Michelson-Morley experiment, the expression for time difference between the round trip times for parallel and perpendicular arms would produce a null result, that is del t is equal to 0, if length contraction occurs along the direction of light travel. This is interesting because the null result of the Michelson-Morley experiment was explained using different reasons. When the experiment result came out, different scientists approached that result in different ways. One of the possible explanations was, of course, a Lorentz contraction. That is, if some Lorentz contraction occurs along the direction of light travel, because we know that length contraction expression, Lorentz contraction expression, Lorentz, let's call that length contraction, of course, is given by, for a length of L naught, let us say, if the object travels at a speed v, then we know that its length contracts to L, that is equal to L naught multiplied by 1 minus v squared over c squared. So please do check out our videos on length contraction. We have derived, so there is a video derivation of length contraction, Lorentz length contraction. So please do check out that video as well, if you have not watched it already. So this is expression. So here we have to prove that the null result in the Michelson-Morley experiment, which would mean that the time difference between the parallel arm and the perpendicular arm, that is light travel along the parallel and the perpendicular arm, is del t, that is equal to 0, can also be due to the length contraction along the direction of light travel, if that can be assumed. Yes. So let us say that del t is equal to two time differences, that is t2 minus t1, that is a time difference, and that is equal to, in our original expressions, 2 over c. We have been using L, let us call that L2 in that case, L2. square root of 1 minus v squared over c squared minus the other length, let us call that as L1. That is 1 minus v squared over c squared. This derivation we have done. So please do check out the video on the lecture video on Michelson-Morley experiment as well to understand how we arrive at this one. We have calculated the time differences and derived expressions for that in that particular video. So the links for these videos I post in the description of this video. So please go and check out those videos if you have not watched those. So 2 over c, the first term L2 over square root of 1 minus v squared over c squared corresponds to light travel in the perpendicular arm, that is in an arm perpendicular to the direction of the motion of the earth through ether. So there is no length contraction. But in the second term, we have to now assume the length contraction. That is, this L1 contracts to L1 times square root of, let us call that L1 times the square root of 1 minus v squared over c squared. That is due to length contraction. If that happens, then we have, that is length contraction term in the second term here, that is for the parallel arm along which is along the direction of the light travel. If that happens, then we know that we can simplify this further as 2 over c L2 over square root of 1 minus v squared over c squared minus L1 over square root of 1 minus v squared over c squared. So here if L1 is equal to L2, because if the arms are of equal length, which was 11 meters in the original experiment of 1887, then these two terms become same. In that case, del T is equal to 0, right? So the null result would imply that the time difference between these two arms, light travel in these two arms, is 0, and that can also be accounted for by assuming that there is a length contraction. That is what is this question all about. So this question, that is what is being asked. So if length contraction occurs along the direction of light travel, then it is possible to show that in the Michelson-Morley experiment, the time difference goes to 0, thereby accounting for the null result, right? So that concludes, I think, our problems on the Michelson-Morley experiment. So please do check out both part 1 and part 2 videos for solving problems on the Michelson-Morley experiment, as well as the original lecture video on the Michelson-Morley experiment, so that for the students, complete understanding can be obtained. Thanks for watching.